Welcome back, and in this video we're going to talk about divergence and what that means. But as a warm-up question, here we go. Go ahead and just take a shot at it and resume the video once you've completed it. Okay, well, if you recall, this is the same as curl, and if we do this out, right, I always set up a determinant, I, j, k, and then we have the partials, d dx, d dy, d dz, and then we have the components of the vector field, x squared y, z, and x squared, and then we go ahead and do this. Okay, so then I get I, and then let's see, that'll be 0 and 0. Great, that's fun. Oh, I'm sorry, 0 and minus 1. Try that again. And then we have minus j, and then let's see, that'll be 0, and that'll be x squared, and then plus k, and then let's see. Okay, so then we have 0, and we have x squared again. And let's see, minus x squared. And it must be quite a while since I've done this because I made a mistake back in j. This should be 2x, because we do d dx of x squared. So 2x. Okay, there we go. And of course you can rewrite and go on. Okay, but so this was the gradient across the vector field. What do you think about the gradient dotted with the vector field, right? We can do this because remember the gradient is, or not the gradient, but the del operator, right? We know that this means precisely the partial, so d dx, d dy, x1, and I should do x2 because we might have n variables, and so these are just the partials up to a finite position. Okay, and so then if we think about a vector field in n dimensions and we do the del operator dotted with the vector field, well, we know according to our understanding of dot product that this should be dg1 dx1 plus dg2 of dx2 plus so on and so forth up to dgn dxn. Okay, so it's just really the partials dotted, or so the partial derivatives of each component added together. That's all it is. But then remember that when we do dot product and cross product, we get something that's very different, right? We know that generally, when we do the gradient dotted with f, this is a scalar, versus when we do the gradient, or the del operator across f, and I wrote a vector sign there. Some people do, some people don't. Del operator across, this is a vector, right? And so that's one thing to keep in mind. Okay. The other thing is that when we've seen something like gradient of f, right, here, when we're doing this, something like this, this is still going to be a vector, right? The whole thing's going to be a vector. But here, there is no dot product, but the inputs are different, right? So here in this one, this is a vector field, versus in this one, when we do the gradient, or sorry, the del operator on a function, right? The inputs are different. Okay, so we either have vector field input or a function input. Okay. All right, so now it's probably time that we actually define what this gradient, or the del operator dotted with f is, and that's what we call the divergence. Okay, it has a special name, kind of like the curl, and so really it's just what we said above. Algebraically, we haven't talked about the geometric interpretation yet. Okay, and so when we think about this as an operator, if we want to do that, what we have to start with is a vector field. Okay, so our input is going to be a vector field. And I spelled that incorrectly. Because we have to have some vector field input, and then the gradient, or the del here, is really an operator. Okay, and then when we look at the output, well, we get a function, which we think of as a scalar function. Okay, so just an comment on that. And in the later videos here, what we're going to do is kind of explore what divergence is. There's going to be a lot of examples, but we're going to focus on the geometric definition after a few more just algebraic examples.